Now, in our previous lecture we have derived the numerical differentiation methods for a data which may be of non-uniform mesh spacing or uniform mesh spacing. In particular, we use the Lagrange interpolation to derive the case of the non-uniform mesh spacing and the Newton's forward difference formula for finding formulas for the uniform mesh spacing. Let us just briefly write down what are those formulas, so that you can use them in some examples. So, for the case of the uniform mesh spacing, we have used the quadratic interpolation and linear interpolation also. Let us see what are the formulas that we got with quadratic interpolation. The starting point for is the Newton's forward difference formula. So, we had written f x is approximately p x, that is equal to f naught plus u into delta f naught plus u into u minus 1 by factorial 2 into the second forward difference delta squared f naught. Using this we have differentiated it and got the formulas for f dash at x naught is 1 upon 2 h minus 3 times f 0 plus 4 f 1 minus f 2. The error for this was error at x naught, we got it as h square by 3 f double triple dash of xi, xi lying between x naught and x 2. It is a quadratic interpolation. So, we are using only 3 points x 0, f 0, x 1, f 1, x 2, f 2. Now, I can similarly find out the formulas for the first derivative at the middle point, that is x 1, and this we have derived it as 1 upon 2 h as f 2 minus f naught, and it is symmetrically placed, x 1 is symmetrically placed between x naught and x 2, and the error in this case was error at x 1 is equal to h square by 6 f triple dash of xi. And the third formula that we can have at the last point, that is f dash at x 2 is equal to 1 upon 2 h of 3 f naught minus 4 f 1 plus f 2, with the error being the same as earlier, that this is equal to h square by 3 f triple dash of xi. So, these are the formulas that we have derived last time, starting with the Newton's forward difference formula, using up to second difference, because it is only quadratic interpolation that we have obtained over here. And we can see from here that this is a formula of order h square, that means therefore, it is a second order formula. This is also second order formula, this is also second order formula. All the formulas that we have written here is second order formulas. Now, we can use the same formula to get the second derivative also. So, if I can write down the fourth formula that we obtained was for second derivative f dash of x. Now, since we started with quadratic interpolation, that is a polynomial of degree 2 in u, the second derivative will give a constant. Therefore, f double dash x was derived as a constant, simply 1 upon h square delta squared of f naught. Therefore, and we have shown that the error is only of order h, error is of order of h, therefore, this can be only a first order formula. Now, to find the order, it is not necessary that we should remember this particular formula, error formula, and then derive it. When once this formula is given to us, I can just use the Taylor expansions about the point that is given here. So, this point here is x naught. So, I can expand f 1, f 1 means f at x naught plus h, f 2 is f at x naught plus 2 h. So, for I can substitute this here, write the Taylor expansion of this, cancel all the terms, the leading term will be the term that is given here. So, we do not have to remember all this formula. I can use the Taylor expansions and get whenever required the order of the formula. So, they would all be the same thing. So, let us just number it as 1, so that I want to use this in example. Now, here again I can write down this, if I write this, open it up and write 1 upon h squared is his forward difference f 2 minus 2 f 1 plus f naught. I can Taylor expand it and show that it is of the first order. So, let us take an example on this. So, now I will take a simple theoretical example first. Derive formula corresponding to 1 I mean to say 1 is this particular formula that we have written here, we numbered it as 1 using quadratic interpolation and backward differences. Now, as in the case of the interpolation, here also in numerical differentiation we need the formulas for the backward differences also. The reason being, if we are at the beginning of the data and we want the derivatives at any intermediate point or this, then I can use these formulas or this formula that I have written it writing f dash x here. But if we are at the end of the table, then forward differences are not available for us, therefore, I cannot use the forward differences. So, when I want to find the derivative at a point at the end of the data, I need to have formulas using backward differences. Therefore, the starting point for this is again that we just write down the polynomial in terms of the backward differences. So, it will be f n plus u backward difference with respect to delta f n, this is half u into u plus 1 delta squared f n. So, this is the formula that we have derived for the Newton's backward difference formula, and the error for this was derived as 1 upon 6 u into u plus 1 into u plus 2 into h cubed f triple dash of xi. We have used it is a quadratic interpolation. Since it is quadratic interpolation, we have taken only up to the second backward difference, and the error is of this particular form. Now, I can differentiate this and write f dash of x is equal to p dash of x, approximately p dash of x. The derivative is 0. So, this is delta f n. Now, plus I am using derivative with respect to u into delta u by du by dx, that I will write it, and this is equal to half u square, that is 2 u plus 1 delta squared f n into you remember what is the formula for u was x minus x n divided by h. Therefore, du by dx will be equal to 1 upon h here. Now, this formula we shall use whenever we want to find the derivative at any arbitrary point at the end of the data. X we can find out when once x is given, I can find out the value of u from here, substitute it over and get the derivative. Even though this formula would get simplified if I take the nodal points, that is either x n or x n minus 1 or x n minus 2. I can find formulas using at the nodal points. Now, if I write the error, what will be the error at this point? I can differentiate this error as error at x is 1 upon 6. Now, again I am differentiating with respect to u and then 1 upon h. So, let us write down 1 upon h first, that is du by dx, h cubed also let us write in first, then I differentiate this as a product. So, I will have d upon du u into u plus 1 into u plus 2 into f triple dash of xi plus u into u plus 1 into u plus 2 d upon du of f triple dash of xi. Therefore, in the general case this will look like h square by 6 into this quantity in the bracket. Now, at the nodal points again this formula simplifies, because we know at the nodal points this is going to be 0. So, let us derive at x is equal to x n. That is what we have been asked in the problem, derive the formula corresponding to formula 1 of this one. Now, at x is equal to x n, if I substitute it here I get u is equal to 0. So, that means this is equal to u is equal to 0. Now, therefore, let us substitute u is equal to 0 in this. F dash at x n is backward difference delta f n plus u is equal to 0. So, I will have delta squared f n into 1 upon h. Let us simplify this. 1 upon h, this is f n minus f n minus 1 plus half f n minus 2 f n minus 1 plus f n minus 2. Therefore, this is 1 upon 2 h, this is 2 f n plus f n 3 f n minus 2 f n minus 1 minus 2 f n minus 1 minus 4 f n minus 1 plus I have f n minus 2. This formula looks very similar to what we have here in the formula 1, except that the suffixes have been changed and it is reversed. So, we are this formula is coming from this side from x naught inside, whereas from this formula we are coming from x n inside in the opposite direction. That is how the directions get changed here. Now, let us find out what is the error at x dash at x n. Now, outside we have h square by 6. So, let us have this out square h by square, u is equal to 0, therefore, the second term goes off. Now, I differentiate this as product of 3 terms, only one term will survive, which will be the derivative of this particular part. Derivative of this is this product, if you just put u is equal to 0 I will get a 2. So, I will get a 2 here and f triple dashed of xi. So, the error is again as we have in the previous case h square by 3 f triple dash of xi. Okay. Let us actually take an example on this. The following data for f x is equal to x to the power of 4. Let us give the function also, so that we can understand about the error is given. Point 4, 0.0256, 0.6, 1296, 0.8, 4096. Find f dashed 0.8 and f double dash 0.8 using quadratic interpolation. Obtain the bound on the truncation error. And since exact solution is given, let us compare with the exact solution also. Now, we are asked to find derivative at 0.8. 0.8 is the last point of the data, therefore, I need to use the backward differences. That is the formula that we have just now derived. I must use this formula to find derivative at the last point. That means, f dash at 0.8 is 1 upon the step length that is given to us is 0.2. So, that is 2 into h, that is 0.4, that is 3 times. Let us write down the expression. This is, let us take f naught, f 1, f 2. So, this will be 3 f 2 minus 4 f 1 plus f 0, 3 f 2 minus 4 f 1 plus f 0. Now, let us substitute the values. So, that is equal to 1 upon 0.4, 3 times 4096, that is f 2, 4 times f 1 1296 plus f 0 0.0256. I can simplify this, the value is 1.84. Now, I need the second derivative also, f double dashed 0.8. Now, again from the previous formula, the previous formula that we have here is, we have written this, if I differentiate it once more, f double dash, probably I could write just right here and show this, that will become, derivative of this will be simply equal to 1 upon h delta squared of n into h 1 upon h, therefore 1 upon h. I am differentiating with respect to u, therefore du by dx will also come 1 upon h square delta squared f n, which corresponds to the formula in the forward difference 1 upon h square forward difference formula at 0. Therefore, what I have here is 1 upon h square, that is 1 upon 2 whole square, our step length is 0.2 and this is your delta squared of f 2. We will have here delta squared of f 2. Therefore, I can write this as 1 upon 0.04 delta squared f 2, that is equal to backward difference. So, I will have f 2 minus 2 f 1 plus f 0. So, let us substitute these values, 1 upon 0.04, f 2 is the last value 4096 minus 2 times the middle value 1296 plus f 0 is 0.0256. Now, I can find out its value, it comes out to be 4.4. Now, let us first of all see what is the error by using the exact solution. The exact solution is f dash, let us differentiate it, that is 4 x cubed, and for second derivative f double dash is 12 x squared, and we need for the error also, let us write down the third derivative, that is equal to 24 x. Therefore, the exact solution is f dash at 0.8, that is 0.8 whole cubed. I have the value here, that is 2.048. Now, let us, before we find the second derivative, let us now find out what is the error. The error is 2.048, that is the exact solution, minus 1.84 is the solution which we have got here. So, this is equal to this subtract 1.84, therefore, you have got here 0.28. 0.28 is the error, it is quite large error. Let us see why it is happening, we can find it out. Now, let us find the exact solution, second derivative f 2, that is 12 into 0.8 whole square, this is 7.68. The error in this case is the exact solution 7.68 minus the numerical solution that we have got minus 4.4. Therefore, the error is 3.28. These are the actual errors in the problem. Now, let us see what our theoretical values of the error tell us. Now, the theoretical expression for the first derivative error is is h square by 3 f triple dash xi. Therefore, let us try to find out the error from this. Therefore, the magnitude of the error at 0.8 is less than or equal to, I am writing from here, h square by 3 m 3. m 3 is the maximum of f triple dash of x in the given interval. The given interval is 0.4, 0.8. So, in this interval. Now, we have found out the value, third derivative is 24 x. So, I can find out what is m 3. m 3 is maximum of within the interval 0 to 0.8. The third derivative is 24 x. Therefore, this is 24 into 0.8, that is equal to 19.2. So, it is because of this reason our actual error is large, and our the numerical value also shows that it is the error is going to be large, because m 3 is very large. So, let us write down, substitute it here. Therefore, derivative error at the derivative is point h square is 0.4 divided by 3 into 19.2, that is 6.4 into 0.036, that is 0.256. Now, you can see that the actual error is 0.208, and the theoretically it is predicted that the error is going to be 0.256. So, the actual error is always less than this, because this is the maximum possible error in the problem. Now, let us derive the expression for the error in the second derivative. H is less than or equal to h upon h into m 3, and this is equal to 0.2 so this gives us 3.84. Now, this is the error that is predicted by, and the actual error is 3.28. So, again the actual error is less than the predicted error. Therefore, we given a data, and the point at which we want the derivative, a first derivative or the second derivative. If it is at the beginning of the data, we shall use the forward differences. If we are at the end of the data, we shall use the backward differences. And using this formula, we could have computed not necessarily the solution at 0.8, we could have find the numerical solution at any intermediate point also, but then we shall be using the original formula that we started with. For example, if I want to find the what will be the derivative at 0.7, I shall be using this value by finding what will be the u. For example, if you are asking for what will be the value at f dash at 0.7, then I will be using finding out my value of u. U is equal to x minus x n by h, and here x n the last point is 0.8, and the step length that is given in the problem is 0.02. So, this will be minus 0.1 by 0.2, that is 1 by 2, that is minus 0.5. Therefore, u, the value of u would be minus 0.5, and I shall be using this value of u in this expression to find out what will be the value of the derivative at a non mesh point. So, any point intermediate in the point. So, I shall use this formula directly by finding u and substituting over here. Same thing is true for the other derivatives also. The formulas that we have derived so far can also be derived alternatively by using the difference operators. If you remember that we have derived the difference operators, we have defined mainly the operators E, the shift operator, forward difference, backward difference, central difference. We just need the definitions to derive these formulas. E is equal to 1 plus delta, E is also equal to 1 minus backward delta minus 1, and delta is e to the power of half minus e to the power of minus half. These are the relations that we have derived between these operators. Now, we have also derived the relationship between the dy by dx derivative operator and these operators. Let us just re-look into that particular aspect. If I write down E of f x, which gives me the shift by one unit, that is f of x plus h, let us write the Taylor series of this. So, this gives f x plus h. Now, I will use the d for d by dx. I will write down notation d for d by x. Therefore, instead of f dash, I will write down d of f x, h square by factorial 2, second derivative, that is d of d, d square of f x, and so on. So, this is my Taylor series. I will now write this as 1 plus h d, h square d square by factorial 2 and so on, operate on f x. So, I have taken the f x on to the right, so that I operate on f x this particular operator, and this symbolically I can write this as exponential of h d, operate on f x. So, if I open up exponential of h d, we will have 1 plus h d, h square h d whole square by factorial 2, h cube d cube factorial 3 and so on. So, whatever is there in the bracket is the symbolic expansion of exponential of h d. Therefore, the operator E must be equivalent to the operator exponential of h d. Therefore, the operator E is equivalent to exponential of h d, or if I take logarithm on both sides, h d is equal to log of E. Now, it is this that would give us the formulas that we have derived here. So, my starting point is here. So, I take h d is equal to log of E, but E is 1 plus delta. If I want the forward in terms of forward differences, I will substitute E is equal to 1 plus delta. So, I will write this as log of 1 plus delta. Then symbolically open up logarithm. This will be delta minus delta squared by 2 plus delta cubed by 3 and so on. We have numbered earlier 1, let us number it as 2. Now, if I want backward differences, I will now use E is equal to 1 minus delta inverse. So, I will write this as logarithm of 1 minus backward difference inverse. Let us take minus 1 out. So, this will be minus of log of 1 minus delta. Now, let us expand this logarithm. This will be minus delta square by 2 and there is a minus sign outside. Therefore, all of them would be positive, delta square by 2 plus delta cubed by 3 plus so on. That means, if you operate it on any given function f x, now that will be simply either I have delta square by 2, delta cubed by 3 and so on, operate on f x, or I will have this as backward delta square by 2, delta cubed by 3 and so on, operate on f x. Now, I can get the formulas by just cutting this series at one term. I can cut it after 2 terms, I can get it after 3 terms and so on. So, all the formulas that we obtained earlier can also be obtained from here. If I use only one term in this expansion, I will get first order formulas, that means order of h formulas I will get. If I use 2 terms, that means I am using up to delta square by 2 here and backward difference square by 2, then I will get all second order formulas, order of h square formulas. whatever we have derived earlier using the forward or the backward differences are obtained using this particular formula also. But there was one formula earlier which we have derived at the point middle point, which we have shown it as symmetrically placed f2 minus f naught by 2 h. Now let us have a look at how that formula can be obtained, and that for that I will use the central difference, this particular formula, the formula that we have written. We have delta is equal to e to the power of half minus e minus half, but e is equal to exponential of h d. So, I will write down exponential of h d by 2 minus exponential of minus h d by 2. Now, this is of the form some exponential of x minus exponential of minus x, that is equal to 2 sin hyperbolic x. So, I can write this as 2 times sin hyperbolic h d by 2. Now, I can bring 2 to the left hand side and invert this to find h d. Therefore, h d is equal to, let us take 2 also to the right, 2 times sin hyperbolic inverse delta by 2. We bring 2 to the denominator, invert it, sin hyperbolic inverse h d is equal to 2 sin hyperbolic delta by 2. Now, the expansion of sin hyperbolic, the first 2 terms is same as sin inverse. The first 2 terms of sin hyperbolic inverse is also same as first 2 terms of sin inverse. So, let us write down those 2 terms, that is sin inverse is sin inverse x is x minus x cubed by factorial 3. So, that will be delta by 2 minus 1 upon factorial 3 into delta by 2 whole cubed. The first 2 terms will be the same. That means, I can write this as delta minus 1 upon 24 delta cubed. This is 8 into 6 48, you have a multiplicative factor here. So, this is the derivative, first derivative in terms of the central difference. Now, if I want the second derivatives is almost trivial, because what we are looking for is d square. So, if h d gives me this, I can operate pre multiply by h d. Therefore, h square d square will be operator square operator square. Therefore, if I want the second derivative, I just have to operate on the left by h d here. Therefore, it will be simply the square of this delta square by 2 delta cubed by 3 so on whole square. So, I just have to take the square of this, that will give me the h d operator is being pre multiplied once more. So, I will simply have the square of this operator as this one. That means, this will be, let us open it up, delta squared, the product of this is delta cubed. I am writing the first 2 terms, delta square 2 times this one, that is minus delta cubed plus so on. Now, you can see again, if I cut the first term, what we have done earlier we get it, that is d square is approximately 1 upon h square delta square. This is what we have derived earlier using the forward differences, that second derivative d square, this is your second derivative f double dash, put f here, put f here. So, second derivative is simply 1 upon h square delta squared f, and if I write one more term, I will be using more number of points. Now, I can use similarly the backward differences, just as I have done it here. I can use the backward difference as this, h square d square of f will be square of this backward difference delta squared by 2 whole squared of f x. Therefore, this will be delta squared plus delta cubed so on f x. Now, again whatever we have done earlier, we can get here the second derivative approximation is d squared of f, this is d squared of f, this is approximately 1 upon h square delta squared of f x. So, this was the formula we have derived, f double dash at x n is 1 upon h square delta square of f x n. So, we have got the same formulas again. I can therefore use the next term also, next term is delta cubed. So, I will be using more number of points to get the formula over here. Therefore, the formulas that we have obtained using the interpolation can be obtained by using the difference operators also without any change whatsoever. Now, let us see what will be happen in the third case that we said, method of undetermined coefficients. Method of undetermined in this case, the method that you want depending on the data that is given to us, data is given randomly. So, if you are given a data, you would like to use only those data points in construction of the formula, and let us assume that such formula is not available for you either through the difference operators or through the interpolation. Then what we do is we just write down the formula that we want, use the Taylor expansions, compare the coefficients and find out the parameters that are involved there. So, that is a very simple and straightforward procedure. So, I will illustrate it through an example. Let us take it as an example. Now, derive a formula of the type h f dash x 2 is alpha naught f x naught, alpha 1 f x 1, alpha 2 f x 3, where x I is equal to x naught plus I h, I is equal to 0, 1, 2, 3. As I said, the solution for this is very straightforward. I need the expansion of this about the point that we have been asked on the left hand side. The point we have been asked is x 2 on the left hand side. Therefore, I will write this as alpha naught f x 2 minus 2 h, x naught is 2 units behind x 2. Therefore, x 2 minus 2 h, alpha 1 f of x 1 is 1 unit behind x 2, that is your x 2 minus h, and the third term is x 3 is 1 unit ahead of x 2. So, this will be f of x 2 plus h. Now, I have here 3 parameters alpha naught, alpha 1, alpha 2. Therefore, I need 3 equations to determine them. Therefore, I write the Taylor expansion and compare the constant h square term, because there are 3 parameters, to be determined, alpha naught, alpha 1, alpha 2. Therefore, we need 3 equations, Therefore, compare the constant term, order of h square terms, The next non vanishing term is the error. So, the error is the next non vanishing term is the error term, Now, I will write down only one step and leave it as an example for you. So, if I now write this, open it up, what I would get here is alpha naught f x 2, let us write down suffix 2, minus 2 h f dash x 2 plus 2 h whole square, that is 4 h square by factorial to f 2 double dash. I need error term. So, I will write down the next one also, minus 8 h cubed by 6 f triple dash at 2. This is the expansion of the first term. The second term is alpha 1 f x 2 minus h f 2 dash plus h square by 2 f 2 double dashed minus h cubed by 6 f 2 triple dashed and so on. And the third term is alpha 2 is x 2 plus h, therefore, f 2 plus h times f 2 prime h square by 2 f 2 double prime plus h cubed by 6 f 2 triple prime and so on. Now, I need to compare the constant. There is no constant on the left hand side, that is 0, therefore, alpha naught alpha 1 plus alpha 2 will be 0. So, alpha naught alpha 1 plus alpha 2 is equal to 0. Now, we compare order of h terms. On the left hand side we have 1, h f dash coefficient is 1. So, let us write down 1. On the right hand side h f 2 dashed is minus 2 alpha naught minus alpha 1 plus alpha 2. So, I have minus 2 alpha naught minus alpha 1 plus alpha 2. Then we compare order of h square. There is no h square on the left hand side, therefore, I have the right hand side as 0. Here we have got here h square f 2 double dash 4 by 2, that is 2 alpha naught, this is half alpha 1 half alpha 2. So, I have got here 2 alpha naught plus half alpha 1 plus half alpha 2. Now, I can solve this for alpha naught alpha 1 alpha 2, it is determined. Now, if you look at the error now, the error would be now the next non vanishing term, the next term is minus 4 by 3 alpha naught minus 1 by 6 alpha 1 plus 1 by 6 alpha 2 into h cubed f 2 triple dashed. So, we can substitute the values of alpha naught alpha 1 alpha 2 in that and then write down that this is the error in this particular formula. Therefore, given any particular formula which is required in a particular application, one can use the Taylor expansions, determine the parameters that are there and then find out the error expression also. Now, we have been commenting in the last lecture that the numerical differentiation could be an unstable process, and the reason is that the round of errors can seriously affect these computations. What do we mean by this? Let us just see, let us say what is the effect of round of errors. And the other error, that is truncation errors. The effect of round off and truncation errors. Now, I shall illustrate it through an example as I have done in the previous case. Let us take any particular formula. Let us take the formula that we have derived using the forward differences. This is approximately 1 upon h square f x 2 minus twice f x 1 plus f x 0. Now, we have given the error expression for this already. So, let us take this error for this as a truncation error is equal to h f double dash of xi lying between x naught and x 2. As I said, given a formula, we do not have to remember what is its truncation error, we just write down the Taylor expansions of these terms about the point that is given here, that is your x naught. So, I can open it up, cancel off all the terms, and then the whatever the leading term of the error will be my truncation error. So, that is my truncation error. Now, if I add the truncation error, I should get the, here I put in approximately, it will become exact. So, I add the truncation error to it, whatever error is there I add it to it, I will get the exact solution. That means, f double dash at x naught is equal to 1 upon h square f of x 2 minus twice f of x 1 plus f of x 0 plus the truncation error h f double dash of xi. Now, let us assume that there is round off error. So, let us say there is round off errors. Let us take epsilon 0, epsilon 1, epsilon 2, the round off errors in f0, f1, f2. Of course, if it is a data that is given to us, then if the entire data is accurate to 4 decimal places or 6 decimal places, correspondingly epsilon will be, say if it is 4 places, we may say that it is error is 1 into 10 to the power minus 4, or if you are using round off, then you can say 5 into 10 to the power minus 4. So, we will be able to tell, it will be plus minus, we will be able to say what is the round off error in a given table of values, when once we have said that you have got a 4 place accuracy, 6 place accuracy and so on. So, we know these expressions, but alternatively we can have also that the errors in each one of them could be different also. So, let us take the general case when the errors are this one. Therefore, in actual computation it is not fx2 that is being computed, but fx2 plus epsilon 2 is the error. Therefore, what we are actually getting here in the computations is 1 upon h square f2 plus epsilon 2 minus 2 times f1 plus epsilon 1 plus f0 plus epsilon 0 plus, let us write down this as TE for truncation error. Therefore, this is equal to 1 upon h square f2 minus 2 f1 plus f0. Now, I will write this as round off error plus truncation error, where the round off error is whatever is corresponding to round off error. That means, round off error is 1 upon h square epsilon 2 minus twice epsilon 1 plus epsilon 0. So, I collected the terms from here, 1 upon h square epsilon 2 minus 2 epsilon 1 and this, and the truncation error is we have here. Now, you can see, let us find out what is the magnitude of this round off error. So, the magnitude of this round off error is less than or equal to 1 upon h square magnitude of epsilon 2 twice magnitude of epsilon 1 plus magnitude of epsilon. If you call this epsilon as the largest of all this, this I can simply write this as 2, 3, 4 times epsilon by h square. And what is the magnitude of truncation error? The truncation error is h into, I think I had written it wrong, it is f triple dash. This truncation error is h f triple dash xi, therefore, this will be h into m3. M3 is the maximum of f triple dash of x. Now, you can see why we were so much worried of the round off errors. If you look at this quantity, this round off error is being divided by the step length h square, whereas truncation error we are multiplying by h. Now, if in a, what we mean by convergence we are speaking of, we are saying that if you are given a table of values with a step length say 0.5, if I reduce the step length by a factor, then it will be much more accurate. That means, as h tends to 0, if you take smaller and smaller step length for constructing a table, then it will be more and more accurate. It is true, because truncation error would always tend to 0 as h tends to 0, because this is always going to 0. Therefore, truncation is always going to 0. Therefore, if you use smaller and smaller step length, yes, we are going to get better accuracy. But if there is round off error in the problem, what would happen? As h tends to 0, round off error can blow up, because we are dividing by h square. We know what is our epsilon, which may be 10 to the power of 4 or 10 to the power of minus 5 by h square, but this is where the whole difficulty is. This tends to infinity as h tends to 0. You see, for example, if you are taking say epsilon is 1 into 10 to the power of minus 4, then if you are taking this epsilon as 1 into 10 to the power of minus 4, this would imply this is 4 into 10 to the power of minus 4 divided by h square, depending on the step length. Now, you can see that if h is smaller and smaller, going to 0.01, 0.001, this is going to be very big quantity, and therefore, the round off error can blow up, and it can really play havoc in the finding the numerical solution. And hence, we say this numerical differentiation can be an unstable process. Now, we are going to analyze this further and give concretely the quantity or what is the total error that we are committing in any particular problem. Given a formula, we shall be able to say exactly what would be the error in terms of epsilon and how it is going to behave it. Then we shall take it in next class.